All right, hey guys, today we are going to talk about light waves. We kind of talked about sound waves for the last couple days, and now we're going to talk about light waves. So, the big difference between sound waves and light waves that I need you to kind of know right from the beginning is that sound waves are mechanical. They had to have a medium to travel through, right? We did the tuning fork lab. The sound had to travel from the tuning fork through the air to your ear. They cannot travel through empty space. Light, on the other hand, can. Light is an electromagnetic wave, can go through totally empty space. So you see things like books because light in the room reflects from the page into your eyes. And then just like your ears interpret sounds and send those signals to your brain, your eyes interpret images and send those to your brain. So light is really just fast moving energy. Light travels at about 300 million meters per second, way faster than sound. Light is the fastest thing that there is. Nothing travels faster than light. And just to put it into numbers that'll make sense to you, it's about 186,000 miles every second. So think about a mile, 186,000 miles every single second. And the speed of light, because it is the fastest thing in existence, it's really important in physics. So important we give it its own symbol, a lowercase c. So here are some characteristics of light you need to know. Light, number one, as I just said, travels extremely fast and over very long distances, like from the sun to here. It carries energy and it can also carry information. It has color. Anytime you see a specific color, you are seeing one specific type of light wave. It can vary in intensity, which means that it can be bright or it can be dim, depending on several different factors. It travels in straight lines. It doesn't curve. It travels in completely straight lines until something gets in its way. And when something gets in its way, it either bounces or bends around that object. So light is a form of electromagnetic energy. The visible light that we see is part of the electromagnetic spectrum. So light is not just about what we see. There's lots of different other types of light, although we don't really think of them as light because light is just electromagnetic energy. So the electromagnetic spectrum, and you can see it at the bottom of your screen there. The electromagnetic spectrum really just shows you all the different types of electromagnetic waves in order from lowest frequency down here with radio waves that are the furthest apart all the way up to gamma rays, which are the closest together. So most light is produced by atoms, even though the light isn't made of atoms and it doesn't actually need atoms to travel through. But what happens is when atoms have extra energy, they have to get rid of it. So when they have extra energy, they throw it off and it looks to us like light. So in order to get light out of an atom, it's got to have too much energy. You have to put some energy into it first. And then when it throws off that extra energy, we've got light. And the easiest way to do that is to add heat. So generally speaking, when things get hot, they start to produce, and I'm talking really hot, they start to produce light. Think about how things tend to glow when they get really, really hot. And that's called incandescence. So think about a light bulb. Light bulbs seem to glow. And if you look inside a light bulb, don't ever do that. It'll hurt your eyes. But if you could, you can see the little wires start to glow as they get hot. What's happening is we're heating up the atoms. They have way too much energy because they're so hot. They throw it off in light waves to get rid of it. That's exactly what's happening there. Fluorescent light kind of work the same way, only instead of heat, they use electricity. Kind of does the same thing. It just puts too much energy into the atoms, and then they have to get rid of that electrical energy instead of heat energy. They have to get rid of that electricity. And so they get rid of it as light, which is good because those light bulbs are not very hot. There's no heat energy. It's just electric energy. Color is special. Color is the type of light that our eyes can see and process. It can't see or process any of those other types of waves, but it can see light waves, these color light waves. All the colors of the rainbow, there they are down at the bottom of the screen in order. When you put them all together, you end up with white light. When you put all of those light waves together, a red light wave, an orange light wave, when you put them all together, the constructive interference creates what we see as white. So two different colors here. Compare the hot blue flame from a gas stove to the orange flame of a match. The blue has higher energy. The red has lower energy. So that blue flame is hotter than that orange flame. We've talked about this when we talked about stars in part A. If you'll remember, the darker the star, if it was red or orange, the darker the star, the less hot it was, the colder it was. Stars that were blue or white were much hotter, right? Because they have more energy. And if you look at the spectrum down here at the bottom, you start with violet at the bottom, that has the most energy, so that would be the hottest, and then red has the lowest energy. So light energy comes in these tiny wave bundles called photons. These are not particles, they're just little wave bundles. Each photon has its own energy. The energy of the photons is seen as a color. So when you see something red, it's because tiny, tiny, tiny little photons of red light waves are hitting your eyes. Okay, this is just a chart to show you the wavelength and frequency of light. So you can see here that red has the biggest wavelength and the lowest frequency. That means it's got the lowest energy. Its waves are really far apart and kind of gentle. Violet, on the other hand, its waves are really close together. It has a higher frequency, so it's got more energy. So light, what we see as visible light, is just one little part of the whole electromagnetic spectrum. So we also have these invisible waves down here. We have radio waves, we have microwaves, we have infrared light, we have ultraviolet light, we have X-rays, and we have gamma rays. All of those are just moving light energy. That's all it is, but we can't see all of those. We can only see visible light. And here you can see radio and television waves have the lowest energy, the lowest frequency. Their waves are the furthest apart. And then you can see, you can pause it here if you want and look at it all in order, all the way up to gamma rays, which have the most energy. And when you get into ultraviolet light, X-rays, gamma rays, because they have so much energy, too much exposure to those can really hurt your body, because your body is not meant to be hit with that amount of energy. That's why gamma rays turns Hulk into the Hulk, because your body is not meant to have that much energy. Yeah, I would suggest you pause this for a second and check out the electromagnetic spectrum. So we tomorrow are going to talk about light, and then at the end of the week we're going to do kind of a little mini project. It's only going to take one class, where you are actually going to go through the electromagnetic spectrum and kind of individually research each one of these little sections. Research radio waves, microwaves, infrared light, and figure out, if it's not visible light, if we can't see it, then what is it and what does it do? That's where we're going to move into next. I just kind of wanted to give you guys an introduction to light. So your vocabulary word of the day, to prove to me you watched this video, will be photons. I'll even go back to it for you. There you go. That's your vocabulary word, photons. So go ahead and either turn that in on Google Docs or in the Google Classroom, or make a private comment about it so that I will know that you've watched this video. All right, we'll talk about light a little bit more tomorrow. Bye, guys.